Hello everyone. This is a video about the final project report in my machine learning courses, which is CSCI 6364. And I'm Longji Yang. My title for this report is Using Transformer Decoder for News Article Classification. So let's begin. About the statement, news article classification is a fundamental task in natural language processing aimed at automatically categorizing news article into predefined topics or categories. With the exponential growth of digital news content, efficient classification is crucial for enhancing information retrieval, personalizing content recommendation, and analyzing trends and public sentiment. The transformer models, introduced by Vasavani in 2017, represent a significant advancement in natural language processing, excelling in sequence-to-sequence tasks like machine translation and text summarization. Central to the transformer architecture is its encoder-decoder structure, where the encoder processes input sequences and the decoder generates corresponding output sequence. This project specifically delves into the decoder component of the transformer model, focusing on its ability to understand the classified sequence. Leveraging self-attention mechanisms, the decoder captures the intricate dependencies within sequences, ensuring the classification of contextually meaningful text. And this is the structure of the original transformer. In the paper, attention is all you need. We can see here that it has an encoder part and a decoder part. So a connection is built between the encoder and decoder so that it can handle the two sequence. But for my project, the connection between encoder and decoder and also the encoder part will be removed because it's only for classifications. So it turned into like a structure like this. And also because it's for classify, there is, for me, I don't find a way to use the mask mechanism so that the mask mechanism is also removed. By dissecting the decoder's functionalities and exploring its implications for news article classification, this project aims to illuminate the features of transformer architectures in natural language processing tasks, like training time consumption, accuracy, GPU RAM usage, and compare the model's performance with other models like long short-term memory and Word2Vec. So before we start building our model, we have to find the data that we use for training. So I found two data sets on Kaggle. Both are the data sets regarding the news articles, and all of them are well labeled. The first one is BBC full text document classification, and the other one is news article classification datasets for NLP and machine learning. And here is the link. If you have the slides, you can click here and check the dataset. But no worries, we are going to the details of these two datasets. The first one, it has 2,126 rows, and it have two columns. One is data, which contains the text, and another is labels. And it have up to 5 labels. And the other one, it have five CSV files, and each file contain one topic like business, education, entertainment, and so on. And they have 5 columns. For each file, it have up to 2,000 rows. So, but for me, I just pick up the content and the category and turn them into the data and labels which fit for the first one's format. So before we throw the data into the model training part, we have to first merge them together and clean the stuff that we don't want so that the model will have a good ability to understand the context. So first step is that I merge the CSV, and like before I take the content and category from the files and then merge them with the BBC data, and then I remove some unrelated content like there the content still remain some text that is belongs to the website but not the news itself, like subscribe, like login, like register, or advertisement. So this is a pattern that I managed to remove a lot of unrelated content. And also you can see here that I remove the data which is longer than 4,000 because I think the data that is too long may lead to some computational problem, and due to the nowadays large language model, it have a context window like 4096 context length, so I set to the content length to 4000, and finally it come into the merge data CSV. And also it is find out that the two different data sets share some content, share some labels, but the labels are similar but not the same. So I also merge the similar label into the one label. And regarding the modeling, and this project used a transformer model, and it has 6 decoder layer, 8 head in multi-head attention. It have a different vocabulary dimension like 126, 256, and 512. And during the training for different vocabulary size, no, I mean the vocabulary dimension, it will use different batches, and totally it have 6 label for prediction. And for the methodologies, for the coding part of this project, it's referred to the annotated transformer in Harvard website, which link is also shown here. And it's really clear. It helped me a lot to understand each part, each function of the transformer goes. And since this project is for classify, it's no need to use a mask. So the mask is set to none. And for generator, it's switched to the classifier because it's not for generative test. So instead of getting a probability list for all vocab, it turns out that the classifier will finally come up a probability list containing all the labels. And also the structure, which the encoder part is removed, turn into a only decoder part. Regarding the tokenizer and vocab in the transformer, vocabulary represents the unique tokens used for training and inference, encompassing words, punctuation, and special makers like sequence boundaries. Vocabulary size crucially impacts model complexity and resource demands, with large sizes enabling broader expression at the cost of higher computational requirements. It's not a good idea to make every word a token, which might lead to better understanding of the token. Like if I throw a passage which contains the vocabulary that the model have never met before, then it will cause a trouble. So I just use a BERT base case tokenizer from the auto tokenizer in the Hugging Face transformer package, and its vocabulary size is to 28,996. So here is below is the code that I load the tokenizer from the auto tokenizer. And the most important part of the attention is all you need is called attention. It helps to build a relationship between each token. So as we can see here, it has three parameters like Q, K, and V, which represent the query, key, and value, and it's all of them are weighted metrics. And by this formula, we can get the relationship between each token, and it all comes like a matrix. And gathering the attention and for the computational reason, and it become a multi-head attention. So many attention layer have its output, and finally it concat together, and it will throw into the linear part. And before the linear neural network part, then it's called the multi-head attention. Also, the neural network here it will help the different dimension to have understanding to each other. So this is also a key feature of the multi-head attention. Also, there is a mechanism called mask. In self-attention mechanism, a mask is used to prevent the model from attending to certain parts of the input sequence. This is particularly useful in tasks such as language translation, where the model should not attend to the target sequence during encoding. The mask is typically applied to the attention weights, setting them to negative infinite for the positions that should not be attended to. In this project, due to the time and hardware, as well as the goal is to classify but not generate, masking will not be used. And this is the structure of the transformers which used in this project. First, we have the text as input. Then we throw the text into the tokenizer, which is the BERT case tokenizer in auto tokenizer package. No, I mean the auto tokenizer in Hugging Face transformer package. And then the input IDs will go into the multi-head attention, which contain many attention layer, and then it will go into the feed-forward neural network. And the whole structure is called the decoder layer, and it have 6 repeated decoder layer. Finally, it come up with probabilities, and it goes through the software output, and then we get the predictions that we want. And then in this section, I will first compare the transformer models I train with different vocab dimension to each other. Then I will compare the model I train to some other models that I found in Kaggl's dataset page. However, all the other models are found in the BBC News dataset, which is a smaller dataset compared to another dataset. So to begin with, let's see the accuracy in different dimension, vocabulary dimension. And maybe it's not well trained or due to some other reasons that the higher dimension doesn't seem to have a higher accuracy. And for the time consumption, because I use a larger batches in the smaller D model size, so it takes less time for smaller D model size. Like for 126 D model size, and 256 model size, the time it consume doesn't is no more than an hour, but for 512 model size, it takes more than an hour and a half. And I also compare my models with the other models like long short-term memory, virtual back long short-term memory, term frequency inverse document frequency, uh, linear SVM in the aspect of epochs, training times, and accuracy. And I also draw a graph in Python. Um, and I also use log scale here, and so that you and I can have a better understanding of the performance. So about the analysis, based on the accuracy, the transformer models have a gain a good performance on accuracy. And I believe it's also possible that the accuracy will increase if I train it in a larger epoch. And however, it's also shown that the classic NLP model have an excellent ability on task classification. And regarding the training time and GPU usage, it's quite a drawback for the transformer because all those NLP model, it takes really a short time, except like this. I don't know what the reason, but the log time, the time it shows is a quite long time. And I will also like to introduce the advantage of the transformer is that what if we throw a new news which is just written today? Is that this model can predict successfully, can handle the words that it doesn't know? And some recent news articles from CNN and BBC were put into the transformer model I trained, and the models have a good performance on predictions. And two figure here shown that it all predicts successfully. And the first one is an entertainment article, and it predicts successfully. And the second one for technology article, it also predicts successfully. And for the drawback, it takes too much GPU RAM and it takes too much time. So as a conclusion, the transformer models with varying the model sizes like 126, 256, and 512 was implemented and trained on Kaggle Notebook using two T4 GPU with a fixed training epoch of 20. The result accuracies on test datasets were around 98%, around 97%, and around 97.5% for the deep model size of 126, 128, 256, and 512 respectively, showcasing competitive performance across different dimensional scales. Advantage of the transformer model includes its robustness across different datasets, as demonstrated by successful predictions on news articles from CNN and BBC. However, transformers exhibit drawbacks such as high GPU RAM requirements, large storage requirements, and it requires a long time to train compared to the traditional NLP model, like words to vec. And about the potential future direction of this project, and one of the direction is to utilize mask mechanism. Um, so the mask mechanism is to make the transformer model have a better understanding of the context. And I don't use the masks, and I don't know how to use that. But there might be a way that we can implement the mask attention in the classification task. And maybe we can, by utilizing the mask mechanism and train it have a better understanding of the context before and context after. And finally, we'll have a better performance in prediction. And another future direction, potential future direction of this project is to exploring different tokenizers effect. So I just simply use the BERT-based case tokenizers, which is split in the words into, it might split the words into different spoken token like bus, and after that ISS and SS, something like that. So if I choose some other tokenizers, then it might have a better performance. So this is a part that still worth me to try and to research. And this is the reference I use in the essay and during the whole project. Thank you. Thank you very much.